I'm last. Oh, right here.
Thanks. Yeah, so last time we ended abruptly after defining special cube complexes, right? So those were non-positively curved cube complexes that have a local isometric embedding into rags. And we showed that they must be residually finite, like they're linear. And we showed that inside them, one can find many separable subgroups. So yeah, so I think this is where we ended. And yeah, so let's first finish lecture number 3 and then move on to lecture number 4. So what I wanted to talk about a bit is hyperbolic cubulated groups. So if you think about it, if you have this special non-positively curved cube complex, which happens to be, so let's say X, and its pi1 is hyperbolic, then what you can do, well, you have those hyperplanes inside X. So that I'll do a cartoon. Maybe I have this hyperplane. Remember that hyperplanes are embedded, right? So what we can do is we can cut along this this hyperplane and get two new non-positively curved cube complexes that are sort of glued along the hyperplane. Right? So what we'll get out of this is smaller pieces. Yeah. So X or pi1 of X in particular can be written as this free product with amalgamation of the two pieces along the hyperplane.
I missed. Why is there something on the? Is it something that?
We're finishing first lecture number 3,
And then what's it?
and that's our target.
Thank you.
Okay, good. Yeah, so you can split your group along the hyperplanes, but then you can play this game again. Each one of those pieces is again a special cube complex, and you can keep on doing this until you are left with nothing, with trivial groups. So I mean, this splitting can be either as a free product with amalgamation, or maybe as an H and N. Yeah, if you have something like that, right? So here you have one H, one A. So pi1 of X will be in this case an H and N extension. Okay, so this is, I mean, if people are not familiar with this, just think of maybe free products or free product with Z or something like that. But it's a very algebraic way of writing your group, and so this is called I mean, this gives what's called quasi-convex hierarchy. Yeah.
Would you mind writing just a little bit larger?
Sure.
Thank you.
Yeah. So here's this amazing work of. So this was still in Haglund Wise, the fact that you can break
Also,
your.
everything you can't see is at H hat.
Yeah, that's true.
Yeah.
So what Wise tells us is, in fact, everything that can be written in such a way, meaning that has such an hierarchy, is, well, virtually a special non-positive cube complex. So hyperbolic. So let gamma be hyperbolic. If gamma has it's called a virtual quasi-convex hierarchy, then let's put it like this. Then gamma is virtually special, meaning it has a finite index subgroup that's the pi1 of a non-positively curved cube complex. Okay, so what is this thing? This is the smallest class of groups that satisfy smallest class of groups satisfying well, okay, the trivial group is there. V, yeah, the V should be here. That's virtual. Well, okay, whatever. This is in this class of groups, the trivial group. You can do free product with amalgamation or H and N extensions, as long as you make sure that the thing you are amalgamating over is quasi-convex. Okay, so if A and B are in here, and C is class of hyperbolic groups. Okay, follow actually. C is a subgroup of A and B and is quasi-convex in this guy. What did I want to say? Yeah, quasi-convex. Then this guy and this guy. Okay, so free product with amalgamation and an H&N extension should also be in this collection. Okay, and finally, there's this virtual thing, which means that if H is in here and H is finite index subgroup of G, finite index, then G should be in cubic. Okay, so this is, I mean, one direction is what I explained. It's quite maybe easy from the definition, but really the amazing work of Dani shows that that if you have such a hierarchy, then you're virtually special. And based on this, we have the following amazing result of Hegel. That tells us that in fact, if gamma is cubulated and hyperbolic, then gamma is virtually special. Okay, so cubulated again means it acts properly and co-compactly on a cat-zero cube complex, and hyperbolic means Gromov hyperbolic. This is enough to get that it is in fact virtually special, meaning, well, in fact, you can pass to a finite index subgroup such that the same cubulation for gamma would be special for the subgroup. Yeah, and this story will not be complete if we will not give some kind of applications. So really, the big application that made this whole theory such an amazing success story is the case of gamma is the pi1 of a hyperbolic three manifold. So we saw this result of Bergeron and Wise based on Kahn, Markovich, and Sagiv, that those things are cubulated. Okay, say close maybe. Okay, and it's hyperbolic. Well, then the result is that gamma is virtually special. Okay, so maybe the fact that it's residually finite is not that surprising or linear because it was already a hyperbolic three manifold. But what is useful is knowing that certain groups are separable. So from this, one can get what's called virtual Haken conjecture. So what does it mean? It means that M has a finite cover which has a surface, an embedded surface, which is pi1 injective. Okay, so and this is such a thing, a three manifold with a embedded pi1 injective surface is called the Haken manifold. This was like a big thing because people did not know how to solve all sorts of conjectures in three manifolds, and they sort of based a lot of the theory on this idea of having Haken or virtual Haken. The end of the story, somehow the big problems were solved by geometrization, but this is still this amazing result of this work. And another thing is this is quite, I would say, elementary to deduce this from what we already have done, but here there's some more work of Hegel showing that the virtual fibration conjecture So M has a finite cover, which fibers over a circle or over a circle. Over S. Okay. Done with lecture number 3. Great. So really the goal now, so we sort of understand that cubulated hyperbolic groups are this nice thing that we want. They're virtually special. They have all the nice properties we talked about last time. And you might ask, okay, what about other cubulated groups? I mean, what happens when we leave this hyperbolic setting? Let me just mention this result of Kapras and Sagir. I think it's very relevant here. It's the rank rigidity for Ket-zero cube complexes, and so it states the following. So this is one version of it, maybe the one that's less used, I think. So X is what do I want to say? Yeah, some locally compact, geodesically complete. Geodesically complete means every geodesic segment can be extended to a ray. Geodesically complete. Yeah, Ket-zero cube complex. Okay, then wait, no, I need a group acting on it. So at gamma tonic geometrically, so properly and discontinuously. Properly and co-compactly. Right. Then really we have two options here. So either X is a product. Okay, so that's one option, or X, or I should say maybe gamma, has a rank 1 isometry, meaning there is an element of gamma that acts on X with an axis. Okay, so it moves along some axis in such a way that this axis does not bound any half flat. Okay, so there's an axis, let's call it L, with axis L, such that L does not bound a copy of half of a Euclidean half. This is bad. Okay, and so really the world divides into, I mean, if you are not hyperbolic, you still have some kind of hyperbolicity in the form of this rank one isometry, or you're a product, right? And under this assumption of rank 1 isometry, one can actually show that gamma must have some quotient. So gamma, so if gamma is not, if we are not in the product case, I don't understand. Gamma has rank 1 isometries, implies that gamma is not simple. So you get some quotients. Maybe it could still be non-residually finite, but you get some quotients. Okay. And this really leads us to the fourth talk, which is about finding cubulated groups which are simple. Yeah. Quasi-convex virtual hierarchy. Yeah, so we want to find simple cubulated groups. Okay, so we know where to look for those now. After, I mean, this you should know that this was much later than discussed, but we know that if there is any chance they should be in products, and in fact, what we'll see is that they arise in even the simplest possible products, meaning the product of two trees, right? That's the simplest kind of product you can form in this setting of Ket-zero cube complexes. So yeah, so now we're ready to start lecture number 4. So this was not really the goal. What was it? Let me hint. Yeah, no. Anyone? Huh?
That's what you're gonna do.
Yeah. So BMW stands for Burger Moses Wise. I think this is something that Capras came up with. Yeah. I don't know, maybe there's also a Canadian thing called BMW. I did not really look for one. Good. Yeah, so the goal, as I said, is find a simple. Okay. Yeah, I didn't say. I mean, the reason is those are WPD elements, and you can get a cylindrical hyperbolicity, and then you get quotients. A lot in this arrow, maybe. So, although I'm sure that for cubulated groups, you probably don't need to go through that. You can use Wise small cancellation theory for whatever. Yeah. So what are BMW groups? The BMW group is a group in the product, sorry, acting on a product of two trees. So it's in the product of out of two trees. Those are, let's assume, yeah, I mean, that it will follow, but the regular trees, finite balance. Which acts vertex transitively on this part. Okay, so in the quotient, I'll see just one vertex. No, this is not what I want to write. So that, I mean, that's also true, but I want something stronger. Acts simply transitively on vertices of, so on vertices. So simply transitively means freely and transitively on vertices. Yeah. Stabilizers of vertices are trivial.
What's the operation between those?
What's that?
What's the operation between the two homomorphism groups?
This direct product?
It's direct product.
Yeah. It's just, I mean, you should think of this. This is so aught T1 times aught of T2 is basically aught of this product. Yeah. Except maybe in this product, you can switch the two factors. So I'm not allowing you to do that. So there's a finite index. Yeah. Okay. Great. So how does one build such BMW groups? So we'll take one model. I mean, there's more than one model for those groups, but that's one that I like. So such a group, gamma, or not all such groups, but there are BMW groups that can be written in the following way. Okay, so they have sets of M generators, which I call A1 up to AM, and another N generators, B1 up to Bn. Okay, these should correspond to the regularities of T1 and T2, M and N. Okay. And they come with relations. So one relation I'll always add is I want all of them to be involutions. And now I need to add relations to sort of form something that would act on a product of trees. And the idea is that as long as the relations are sort of squares, then and some condition, then I can play the same game I played with a Davis complex. I can look at the Cayley graph, right, and just glue in the squares and hope that what I got is a product of trees, right? So here's a condition. So maybe let me put it here as a remark. A cat-zero cube complex, all of whose links, all of links are isomorphic to the complete bipartite graph is isomorphic to the product of the m regular tree times the n regular tree. Okay, so from now on, when I write t something, it will actually be the regularity. So let me also change this here. Okay, so really all I have to care about is I want the relations to be squares, and I want the link to be this thing. If I manage to do that, then in this universal cover, I'll see something that's a product of trees. So let's make sure that this happens. So the way to do that is you just think of this KMN, okay? So here I'll put I call the vertices A1 up to AM, right? And on this side, I'll call them B1 up to Bn. Okay, and this guy KMN is just connect all the edges from left to right. And I want to see all the edges in the link. So, and I want to form it by looking at squares. So what I really am looking for is a partition of the edges of this graph, okay, into 4 cycles. So I can have like A1, B1, I don't know, A2, Bn. Okay, that's a 4 cycle. And this will correspond to the relation which I just read, right? A2, Bn. Yeah, so each such 4 cycle will give me a relation. Okay, so if I can find a partition of the edges of this graph KMN into 4 cycles, this gives me the set of relations. Relations of length 4. Okay, so let's call them R, which I should add to this presentation. Yeah, and note that a 4 cycle for me could mean I go along an edge 4 times. That's fine. That's also allowed. So they're really easy to produce. You can put whatever squares you like, and then decide, okay, I'm done, and then put just edges that you cross 4 times to complete it into a partition. You understand what I was trying to say? Yeah, you can always put whatever data you want and then just complete it into such a partition. Yeah. Yes. Yeah. It's a partition. It's really a partition of this thing. You want all edges to appear once in each in a 4 set. Well, you understood what I meant, right? There's 1 4 cycle in which each edge appears. Yeah, and how do you create this product of trees? And you just look at the Cayley graph of gamma with respect to this generating set. You mod out by a squared, right? That's a sort of a bygone. You should crush this, and you should glue in of the relations. Yeah. So for instance, if my partition is just you take each edge and you make it into a 4 cycle by crossing it no times, what will be the group? Yeah. What? Yeah, some kind of z squared. I mean, it's not really z squared, right? Because I have several of them over here and there, but it will be some product of z mod 2s. Right. So this is like the A's, and some product of z mod 2s. That's the B's, and a direct product. But that's the. I think this is what Talia was really referring. Okay. But those are kind of boring, right? So boring groups that act on the product of trees, and these type of groups that are virtually something that's a free group in one times the free group in another, the lattice in one times another times free group in another are called reducible. So we don't want these guys. So let's define this thing, because we'll use it later. Gamma, a BMW group, or more generally, the lattice is irreducible if, when I project gamma to each one of the factors, m and n, right? This is not discrete. So maybe here at this point I should say this group comes with a topology, the topology of pointwise convergence, and I want those images to be non-discrete. That's equivalent to saying what I said before. It's not virtually a product of something in a lattice in Tm times a lattice in Tn. Okay, and note that I'm asking it for the first factor, but in fact, it's the same for asking for the second factor. So this is not discrete. And it doesn't matter. Yeah. Okay. So now what's going to be our strategy for any questions about this? Is the topology clear? We say the two automorphisms are close if they agree on what they do on like a large ball in my tree. Yeah. Okay. So yeah. So what's going to be our strategy? Should ask if there are any questions. I'm going to ask. Okay. Yeah. So the strategy is for such a gamma, prove. I mean, okay, find gamma such that it satisfies the following two things. Gamma is non-residually finite, okay, which is already challenging, right? I mean, we should avoid somehow special things there. And the second thing, which is maybe even more challenging, is you want gamma. You want all finite index subgroups of gamma to be just infinite, and I'll define this. What's just infinite? Yeah, so a group gamma is just infinite if it is infinite and has only finite quotients. By quotients, I mean non-trivial. Yeah. The gamma is a quotient of gamma. Okay, so we already feel that there is some contradiction between those two things, and this kind of contradiction is exactly what will give us the fact that gamma is virtually simple. Right here. If gamma satisfies 1 and 2, then gamma is virtually simple. So again, virtual means it has finite index subgroup that is, and so it has finite index subgroup which is simple. So let's maybe prove this so that we see how those two properties are combined into simplicity. So yeah, so I mean, what we should do is look at what's called the finite residual of gamma. What's this? This is just the intersection of all finite index subgroups of gamma. Okay, so let's call this guy, I don't know, K. So what do we know about this guy? Well, okay, it's the intersection of all finite index subgroups. So you know, it's, I mean, you can think of it as the intersection of normal subgroups. So it's normal, right? It's normal in my example. Yeah. Okay, but then what? So this is one thing. It's normal. What's the other thing we know about this guy? It's non-trivial, right? Because gamma is non-residually finite. If the intersection was trivial, the same as saying that that gamma is residually finite. Okay, so I have this normal subgroup in gamma, which is non-trivial, which is the same as saying I have some non-trivial quotient of gamma. Okay, but all of those quotients are finite, meaning this guy k must be of finite index in gamma, right? So the just infinite tells me k is finite index. Okay, but now we can sort of play this game with k instead of gamma. So if n, so the claim is that this k is simple. So if I have any normal subgroup of k, yeah, what do I want to say? Some normal subgroup of k, well, k is just infinite. That's my assumption. Then I want to say n has finite index in k. Yeah. Okay. But note that the finite residual of k is in fact the finite residual of gamma, meaning all of k. Right? Because k itself was finite index. Any finite index subgroup of this is also a finite index subgroup of gamma, but we already intersected all of them to get k. So I can say it contains the finite residual of k, which is k. So we showed that any normal subgroup of k is k. Okay, so this is really our strategy is to find such a group which is non-residually finite on the one hand and just infinite on the other. Yeah. So let's start by proving one, and this is again work of because it's a normal. I mean, this is exactly this can be stated. Every non-trivial normal subgroup has finite index, right? It's the same as what's written there. So this guy, the finite residual, is a normal subgroup, non-trivial normal subgroup. So it has. So yeah, non-residual finite BMW group. So this is really work of Wise. Yeah, and here the idea is the following. Is to use separability in the following way. So here's the theorem lemma. If gamma is say BMW group, which is irreducible, okay, what that means, then the subgroup, let's call it, which one do I want? B. No, the other one, A. This guy is, I mean both, yeah, A and B, but let's focus on A. Is not separable in gamma. Okay, this is not quite. I mean, this is not non-residual finiteness, but from this we will be able to cook an example which is non-residual, not residually. Yeah. So why is that? Let's prove this. Yeah. So what we'll prove is the following property. So claim for every finite quotient of gamma, there exists some bi and bj different, right? Those are the generators, yeah. Some two generators of the B side, such that phi of bi bj belongs to phi of a. Yeah, what does it say? It says that in any finite quotient, I will find a pair such that this product is not separable from A in this quotient. Okay, so let's prove this first and then see how we use this to prove the theorem. So the proof of the claim is the following. You look at the kernel of phi. Okay, so this is some finite index subgroup of gamma, and you intersect it with A. Yeah. Okay, so this is some finite index subgroup of A. Right. Now we know that when we look at how, so what is A? A in my tree is, let's say, the vertical stuff that I see there. Okay, so A, and here I see the B's, okay? And the product of trees is sort of built out of those squares. Okay, so if I take elements in the subgroup A, what they do is they fix a vertex of my tree, the B tree. Yeah, T, what was it? N, I guess. So they fix a vertex, and in fact, they're exactly the stabilizer of this vertex down here, right? When I project. So what was my point? My point is that P1 of A is exactly the stabilizer of some vertex in P1 of gamma. Right? Because all of the A's acted vertically in this picture, so on the other tree, they're not doing anything to a vertex. But they are doing something because this group is non-discrete. The fact that it's not discrete is the same as saying that this stabilizer is infinite. Okay, so this guy P1 of A is infinite. But if it's infinite, also this subgroup is infinite because it's finite index, right? Sorry? Yeah, because at the end, what are the open subgroups of this guy? Open subgroups are you fix something, right? Those are open identity neighborhoods. So, for example, fixing a vertex is such a thing. Okay. Okay, so this guy is infinite, meaning in particular, it's non-trivial. It does something. I can find an element in A prime that does something to the tree Tn. Yeah, and if I can find something an element that does something, I can find also the path in Tn that it takes to another path. Right, so there exists some element A prime in A prime such that when this A prime acts on Tn, acts non-trivial. Okay, so it takes some path in Tn to some other path. Remember that it fixes a vertex. Right? So I'm really thinking of paths starting from this vertex. So I have this path that is taken to another path. Okay, let's make this path as short as possible. Okay, if it is as short as possible, it means that all of its prefix is actually taken to the same prefix, and then I have this one extra letter that is moved somewhere else. Okay, those I'm drawing them apart, but there are really two paths in the tree Tn. The picture is really, here is V, I have a path eta, and what A does is it flips Bi and Bj coming out of here. Okay, but now we can sort of draw this picture in the product of trees in my Cayley graph. So I'll put A here. This is what's his name? A prime. Okay. I have this path eta Bi, and I know that this A prime takes Bi to this guy. So in fact, what you can do is you can complete this picture into some kind of like a rectangle tiled by squares. So I have A prime on one side. This is again vertical, so it belongs to A. So there's some element here in A, and this is the rectangle that I get. Okay, but this rectangle represents a relation, right? I can read A prime, then eta bj is the same as eta bi A. Okay, and now just take this relation and apply phi to this relation. What do you get when you apply phi? Well, let's see. I mean, A prime, what happens to A prime? A prime dies. So this whole side is like 1. What happens to those guys? They cancel out. So when you apply phi, you get that phi of, I don't know, bi bj. Maybe there's an inverse, but they're all involutions, so I don't really care, is equal to phi of A. This is what we wanted. Yeah. Okay, so we proved the claim. Now let's prove the theorem. Proving a theorem from the claim. Maybe let me leave it as an exercise. The idea is that really there is this finite set of elements, all the products of bi bj's that are not separated. If they are all separated, you can cook up a finite quotient that will see this, but then it will contradict this claim. Yeah, you see the logic exercise. So this is the end of the proof. And end of the theorem is an exercise for you. Okay, so how do you cook something that's non-residually finite? So we have this guy gamma and this non-separable subgroup. Well, if gamma is residually finite, and sorry, it's not what I want to say. Sorry, look at the double. Take 2 copies of gamma and glue them along A. This is again a BMW group. It's not too difficult to see. Okay, but here is the thing. A is, so another exercise, A is not separable, implies this guy, this double is non-residually finite. And let me give you the hint. The hint is if it is residually finite, then it's Hausdorff in the profinite topology, right? But then look at the involution replacing the 2 things and look at what its fixed points. This must be a closed subset, but it's exactly A. Okay, solve the exercise for you, but good. And now we want to prove, so we are done with non-residual finiteness. And now we need just infinity. So find a gamma, just write just infinity. Yeah. So here the idea where this comes from is really the work of Margulis. The normal subgroup theorem showed that for lattices in semi-simple Lie groups, let's say with trivial center, they must be just infinite. And the same ideas went to the work of Burger and Moses, and eventually to the following very general theorem of Bader and Shalom. So let me state that this is later than Burger and Moses. Burger and Moses proved it for a product of trees, but there is the following much more general theorem that tells you that if gamma is a lattice in some 2 I don't know, locally compact second countable groups. So for instance, some OT T, like that. And the projections pi1, pi I of gamma are dense. So far, I haven't said much, right? I mean, I can take gamma, I can project it and take the closure, right? But here's the extra assumption that one actually needs is that each one of the GIs is, let's say, simple. One needs less, but for us, simple is enough. Then gamma is just infinite. It's not only just infinite, every finite index subgroup is just infinite. So exactly property 2 that we needed. We'll not prove this because this is really beyond the scope of this mini course. You just say that to prove that something is finite, like the quotients that we want to prove here, one actually proves property T and amenability. So, okay, so some deep theory that one should know. I'm doing the marketing for your father. Feels, yeah, sorry.
Sorry, should that say GI instead of G1? That pi I gamma equals.
Yeah, yeah. Thank you. Okay. And so what do we need to do now? Well, okay, we need to find those GIs and a lattice that will project to those GIs and make sure that they're simple. And the way this is done, or the topological simple is enough. In fact, what you need is just non-compact. So they can have quotients, but okay, yeah. So really, the GIs that will appear in the construction are what's called universal groups. So this is something defined by Burger and Moses. Maybe I should have said this whole part is in the work of Burger and Moses. So what are those? You have your regular tree, and what you first do is so this is your regular tree, let's say TM. You color the edges properly with M colors, right? So you do that. I don't know, 1, 2, 3. There is basically one way of doing this up to the automorphism of the tree, right? So I don't really have much choices for how to do that. Okay, so you color it properly with those colors. And now consider some subgroup F of the symmetric group on those colors, symmetric group on M colors. And so the universal group UF will just be all elements, so G in the automorphism group of the tree, such that whenever I look at what G does locally, so it takes a vertex somewhere, it takes the neighbors, sorry, not the neighbors, the edges incident to this vertex, 2 edges incident to the image. So it induces some permutations on the colors. The permutations G induces on colors are in F. Yeah. So for example, if F is trivial, all I'm allowed to do is move one vertex to another, but I have to preserve all the colors. If F is more interesting, if F is the whole symmetric group, this is like OT T, right? I'm allowed to do any kind of permutation. It's like the group that actually is used, or one of the possibilities can be used, is the alternating groups. So we want something as a group that is simple. So really, the group that we're interested in is UAM. Is it clear what's the definition of the universal group? Yeah. So here's a theorem. I'll put Tits here. I mean, this was after Tits, but it's the same proof that Tits gives for OT, is that UAN is simple. It's not simple, it's virtually simple. There is a finite index subgroup in UAN, which is called U+, which is simple. So what is this U+? Well, you can, in addition to those coloring, just pick a bipartite coloring of the vertices, right? It's, again, only one. And if I ask my automorphism to preserve this coloring, this is the U+. Yeah. So this guy is simple. Let me Let me give you a proof of this. It's a very easy fact. Take a normal subgroup. Okay, so there is some element here. Let's call it, I don't know, G. Some element in N, right? It's not trivial. Okay. This G can be elliptic. It could fix a vertex. If it fixes a vertex, well, playing with G and its conjugate to create one that does not fix a vertex, and in fact is hyperbolic. Okay, so without loss of generality, by which I mean up to changing G by a commutator, G is hyperbolic, meaning it has an axis. And here's how you finish the proof from this point. First of all, you look at the fixator of L, meaning the pointwise fixator of this L. Let's call it F, and show, so that's an exercise, show that if you look at commutators of F and G, you get all of F back. Okay, what's the advantage of doing that? Why do we like commutators so much? If G is in my normal subgroup, the commutator will be in my normal subgroup. Right? So in this way, I sort of made all of F sit inside my normal subgroup. And really what's left for me now is to say, okay, U plus of AN is generated by all the translates of F. This is not supposed to be all. Okay, so those are exercises. So this guy is simple. That's good. It's a good candidate for what we want. And what's left for us is the following theorem of Burger and Moses. Which says if gamma is a subgroup of U plus of AN, okay, and N is transitive, so vertex transitive, and non-discrete, and the local action of gamma, meaning the permutations that I actually get in gamma, are AN. Then gamma is dense. Okay, so I mean, this is really remarkable. You have to check that it's vertex transitive. That's easy. Really, the gamma I'm thinking of is the projection of my lattice gamma, right? So I have to check that it's vertex transitive. This I know. Non-discrete, this is like being irreducible, right? This we know. So all is left is to check the local action is AN, and this is something you can do quite easily by putting relations so that I see a generating set for AN. You did all of that, then automatically you satisfy what we wanted. The projection of my gamma is a simple group, is the U plus A. So I have one more minute to tie everything together. We constructed a non-residually finite BMW, right? This was wise. So take a non-residually finite BMW gamma. Okay. And now, whenever gamma sits inside a bigger BMW group, this bigger BMW group will not be residually finite. Right? So what we can do is we can take this gamma and add more generators and more relators to make sure that it also satisfies this. Add generators and relators so that the projections have local actions AM and AN. So you get some gamma prime, a bigger BMW group, and then this gamma prime will be will satisfy 1, which is a non-residual finiteness, and 2, just infinity from this Bader-Shalom theorem. And so gamma prime is virtually seen. Okay. And here, thank you.
Time is related to your lambda with exactly how it is structured.
So, I mean, think of the original gamma as some partition of the KMN. Now just increase M and N, add more squares to make it into a partition. Yeah, I mean, it has to be a partition. Yeah, exactly. In fact, it's so easy that one can produce many such things. And it's like a joint work with Alex Margolis and Ivan Levkovitz, where we count how many such things one can get. For each M and N, it grows something like M times N to the alpha M. So something between two such things. So this is really how many such simple things you can do. And you can count them up to common durability because they're simple. So common durability doesn't really, I mean, there's not much common durability happening. So in fact, this count also works for common durability. How to prove this theorem? What is this local action? You look, so here for each G in this thing, you can look at a vertex and see what is the permutation you get for a vertex. You collect all of those things. This is some subgroup of F. If you somehow get all possible things, this is all possible meaning the entire AN, then what this theorem tells you is you're dense.
You can shrink that and use gradation.
Right, because you just need to add some generators of AN. You don't even have to work that hard, right, to do that. It's generated by, I don't know, 2 elements, 3 elements, whatever. Just put them.
Get something that should simple. I think the condition was every finite like subgroup.
Yeah, I said it, but did not write. But this is true here. Every finite subgroup of gamma is just because it will satisfy the same. How do you know that this guy is infinite?
Yeah.
It contains, so all of the U pluses contain U plus of the trivial, and this is the Coxeter lattice.
Thank you again.